Welcome to this video guide to the key features of SPARKvue software used to collect data from PASCO wireless sensors across the certified PASCO version of OpenSciEd high school curriculum. 15 lessons use SPARKvue software in student investigations and teacher demonstrations. See the resources provided in these lessons for instructions specific to that lesson's SPARKvue-based activities. This video provides a general orientation to SPARKvue features used across multiple of those activities. The most straightforward use of wireless sensors is to simply monitor measurements. While some sensors have a built-in display, any sensor can be connected to SPARKvue software to view its live readings. Launch SPARKvue, and from this welcome screen, choose the sensor data path. Next, connect your sensor. Power it on, and notice that its Bluetooth light blinks red, indicating that it's available to connect. If you're using the traditional installed SPARKvue application, you should see your sensor automatically appear here along the left, with its 6-digit ID shown in SPARKvue, matching the 6-digit ID printed on the sensor itself. Select it to connect. If instead you're using the browser-based SPARKvue PWA, select this Bluetooth button to open the browser's Bluetooth dialog. Select and connect your sensor. In either version of SPARKvue, your connected sensor appears in this list of connected devices, and the sensor's Bluetooth light blinks green, indicating that it's connected and unavailable to other SPARKvue users. By the way, in activities that use multiple sensors, just repeat the connection process for each sensor. The measurements available from a connected sensor are listed in this center column. Ensure that the measurements of interest are checked. In this case, just the sensor's pH measurement already selected by default. Then, select a desired display template in the upper right to specify how you'd like to view the selected measurement. This activity uses the digits template, which I'll select to create a SPARKvue file with that display for the unitless pH measurement. Press the green Start button to begin data collection and view live measurements in the display. Press the red Stop button to end data collection. Other activities use SPARKvue to record and visualize measurements over time, often in a graph display. Many SPARKvue-based activities specify a SPARKvue experiment file to be used for data collection. Each SPARKvue experiment file has been configured for the specific activity, so all you need to do is connect a sensor and you're ready to begin collecting data. Download these SPARKvue files to your computer from a lessons page in PASCO portal. From SPARKvue's welcome screen, choose Open Saved Experiment. Select your downloaded experiment file to open it in SPARKvue. Power on your sensor and connect it to SPARKvue. Use the Bluetooth button here to open the wireless devices screen. In the traditional installed SPARKvue application, select your sensor here to connect to it directly. If instead you're using the browser-based SPARKvue PWA, select this Bluetooth button to open the browser's Bluetooth dialog. Select and connect your sensor to have it appear in SPARKvue's wireless devices screen. In either version of SPARKvue, press Done to return to the experiment file with your sensor now connected. This particular experiment file is configured to show the CO2 concentration over time in a graph display. The current reading from the sensor is shown here in the live data bar, helpful for checking the measurement during setup before you begin data collection. Press the green Start button to begin recording measurements into the experiment file and displaying them in data displays. Each dot in the graph represents a reading recorded at the rate specified here, in this case 1 Hz, or 1 measurement every second. Some experiment files are set up to stop data collection automatically after a specified time. This file will stop recording automatically at 10 minutes, so I'll fast forward to near that experiment time. And without my pressing the stop button, SPARKvue ends data collection automatically. You may have noticed during data collection that SPARKvue automatically scaled the graph to ensure that all the data was always visible. Here, in the graph toolbar, you can scale the graph so that the data fills it entirely by pressing the Scale to Fit button. In this investigation, students determined the CO2 concentrations at 1-minute intervals. While they could read approximate values from the graph axes, the Coordinates tool provides a more accurate method. Press the Coordinates tool button to add a Coordinates tool to a data point somewhere in the middle of the graph. The Coordinates tool label shows the X and Y coordinates of the data point under this gray box. Drag the gray box to another data point, or use these arrows to nudge the tool from point to point. Add as many coordinates tools as you'd like. All the data recorded between pressing Start and Stop comprise a run of data, which the graph legend shows to be named run number 1. Although this experiment has each student group record only 1 run, other activities will involve multiple runs of data recording. To record another run of data, simply press Start again. Recording of Run 2 begins as shown in the graph legend. Most SPARKvue graphs are configured to show only 1 run at a time, so when you press Start to record an additional run of data, prior runs are hidden. However, you can make any run visible by selecting its checkbox in the graph legend. With multiple runs visible in the graph, be aware that graph analysis tools apply to what is called the active run, indicated by a red box in the legend. Make a different run active by clicking its run symbol in the legend before turning on a graph analysis tool. SPARKvue files provided in PASCO portal help students get to data collection and analysis quickly, even in more sophisticated investigations, such as this one measuring the braking force and corresponding stopping time for a wireless smart cart, using its built-in force and position sensors. We'll start with the SPARKvue file for this investigation already open, and my wireless smart cart already connected via Bluetooth. This SPARKvue file has multiple workbook pages. Move to page 2 using these navigation arrows at the top of the page. Before recording force data from the smart cart, with no force applied to its hook, click on the live data bar measurement and select 0 sensor now to define the current reading as 0 newtons. Use this graph of force versus time to determine the average braking force as the cart is pulled by its hook through this friction accessory at constant speed. The Graph Toolbar's Statistics button provides a choice of analyses for the force data. Select Mean to determine the average force over the entire run. To find the average force only when the cart was being pulled, change the cursor from the default Move mode to Select mode. Click and draw a box around the data points of interest, adjusting its size and position as necessary. The mean updates to analyze only the highlighted data points inside the selection box. So the average braking force was 1.44 newtons. Students record this value on paper and later transfer it to the table on page 3 for further analysis. Rename this table column to braking force with units of newtons, and enter the determined average value in the first cell. To measure the stopping time with this braking force, place the smart cart on the ramp up against the end stop, which sets a repeatable starting point. Navigate to page 1 of the Spark Lab for a graph of the cart's velocity versus time. Record a run of the cart rolling down the ramp and coming to a stop with the friction accessory. Adjust the graph to better view the section of data corresponding to the cart coming to a stop. Scale the graph axes manually by clicking and dragging on an axis to stretch or compress it. Move the graph by clicking and dragging in the middle. To determine the stopping time, begin by placing a coordinates tool on the point when the cart first encountered the friction accessory. Click the coordinates tool label to reveal the delta tool, delta for change, to create a second gray box that you can drag to a different data point. The delta tool reports the difference in x and y values between the two data points. In this case, delta x is the stopping time for the cart. Back on page 3, enter the stopping time in the corresponding cell to begin graphing the relationship between stopping time and braking force. Saving a SPARKvue file preserves everything about it, including recorded data and any analyses, allowing you to reopen it in the future to record more data and perform further analyses. To save a SPARKvue file, go to the main menu and choose Save. I'll open another file in which I've already recorded 7 sets of braking forces and corresponding stopping times, shown here in the graph. To determine mathematical relationships between graphed variables, turn on the graph's Curve Fit tool and select a fit type to apply it to the graphed data. We hope this overview has provided a helpful orientation to the SPARKvue features used across multiple high school activities. Don't forget to look to the written or video procedures for a specific activity for detailed instructions, including on using any specialty SPARKvue features beyond those covered in this video. Also, for additional assistance, check out the Professional Learning and Support sections of PASCO portal. Thanks for watching.